Here are the notes for Unit 3.3, Coulomb's Law in 2 dimensions. In our last section, we looked at Coulomb's Law, which quantifies the force between 2 charged objects. Now we're going to look at what happens when we've got multiple charged objects that create forces in 2 dimensions. We're going to start off by reviewing a concept from AP Physics 1 or AP Physics C, and that is the concept of adding vectors. So let's take a look here. Example 1. It says, a boy paddles a rubber raft across a river to the east bank while current flows down the river from north to south at 1 mile per hour. So I have indicated that in my drawing. He is able to paddle at 1.5 miles per hour. He's going east. And I've also indicated the cardinal directions here in my picture. Find his magnitude and direction of his velocity. Okay, so to find magnitude and direction, I'm going to use the Pythagorean Theorem to find r. And then I'm going to use inverse tangent to find theta. And in this scenario, r is 1.8 meters per second, and theta is 33.7 degrees. You could call this 33.7 degrees south of east. We would start at east, and then we're 33.7 degrees south of that. Another way that you could quantify this would be to state the angle as measured from, 0 degrees. And that angle would be 360 minus 33.7. Because again, this angle in here is 33.7. The main thing is that when you write angles and vectors, that you're very, very clear and use a picture to indicate direction. Okay, so let's try an example with Coulomb's law. And here we go. Consider 3-point charges. Q1 is 6 microcoulombs located at 0, 0. Okay, so I have indicated that down here. Q2 is negative 2 microcoulombs located at 0, 3. So I've indicated that. And Q3 is 5 microcoulombs indicated at 4 meters, over 4 meters, up 3 meters. Find the resultant force, magnitude, and direction on Q3. Okay, so first I'm looking at signs, and I notice that Q3 is positive and Q2 is negative, meaning that there's going to be an attractive force, the force of 2 on 3. Okay, then between Q1 and Q3, they're both positive, so that force is going to be along this line. I'm going to have to figure out that angle in a little bit. And I'm going to call that the force of 1 on 3. Now, let's see. To figure out the angle for the force of 2 on 3, that's at 180 degrees. This is perfectly horizontal. For the force of 1 on 3, I would use tangent to find this angle, inverse tangent of 3 over 4. And that gives me 37 degrees. So now I'm going to make some calculations using Coulomb's law. I'm going to find the magnitude of these force vectors. So the force of 2 on 3, I use Coulomb's law, Q over R squared, plug in the values, and I get 0.005625 at 180 degrees. Then I'm going to do the same thing for the force of 1 on 3. I plug in the values, and I get 0.0108 newtons at 37 degrees. Next, what I need to do is I need to think about what it would look like to add these 2 vectors. What would it look like to add these 2 vectors together? And we're just going to take a quick reminder that to add vectors together, I would start with one of them. So let's say I start with 2 on 3, and I add vectors head to tail. So then if I were to add the force of 1 on 3, it's going to look, actually it's much shorter. Let me fix that. See, it's only 0.01. Oh no, I take it back. Okay, let's think about this for a second. The force of 2 on 3 is actually about half, a little more than half of the force of 1 on 3. So I'm going to try to indicate that when I make my little sketch here. Let me get rid of this stuff. Okay, let me try that again. Oh, okay. So the force of 2 on 3, which again is 0.005625 at 180 degrees. And then I'm going to add this 0.0108 at 37 degrees. And what I'm looking for here is the resultant. The resultant goes from the tail of the first vector to the head of the second vector. So I'm looking for that resultant. To get that resultant, what I need is I need the horizontal and vertical components of 2 on 3 and 1 on 3. So what I'm going to do is I'm going to use some formulas from Algebra 2, that the x component is r cosine theta and the y component is r sine theta. So to find the sum of the x forces, or the forces in the x direction, I'm going to take each vector and take the length of it times the cosine of the angle, and do that for the second vector as well. The length of it times the cosine of the angle. And then I'm going to add those values together, and that gives me my horizontal component, which is 0.002975. And I've redrawn it down here. Again, the horizontal component is 0.002975. Then I'm going to do the same thing for the y components. So I'm taking the length of the vector times the sine of the angle, the length of the second vector times the sine of the angle, adding those components together, and I get 0.00648. And that is my vertical component of my resultant vector. Now I can use the Pythagorean Theorem and inverse tangent to find r and theta. So r will be 0.0071 and theta will be 65.3 degrees. This is in the first quadrant, so that makes it somewhat easier to figure out. Okay, let's try another one. Example 3. Find the resultant... let me go back to my convention here. Find the resultant force on Q2, let Q1 equal 1 microcoulomb, Q2 equal -2 microcoulombs, and Q3 equal 3 microcoulombs. The distances are 3 millimeters. So I'm looking at Q2. I'm noticing that Q2 is negative, and the other two charges are positive, so these are attractive forces. This is an equilateral triangle, so I know that this angle is 60 degrees, which means that the angle for F3 on 2 is going to be 120 degrees. So I'm going to use Coulomb's law to compute the forces. So to find the size of the vector F3 on 2, I use K, Q2, Q3 over R squared, and I get 6,000 newtons at 120 degrees. And I'm going to do the same thing for F1 on 3. And I like that magnifying feature, F1 on 3. And so when I compute that, I get 2,000 newtons at 180 degrees. And then I go through the same process. I'm taking the length of each vector, times the cosine of the angle, the length of the second vector times the cosine, the second angle, and I get -5,000. Then I do the same thing in the y direction, r sine theta, and I get the vertical component. Now this vector is going to end up in the second quadrant because the horizontal component, if I started 0, 0, the horizontal component is -5,000 and the vertical is positive 5,196. When I solve for the angle, this 46.1 degrees is a reference angle. It's in the second quadrant. And so the angle that I actually want, as measured from 0 degrees, is 180 minus 46.1, which is 133.9. And again, I can use the Pythagorean theorem to find r. R is 7,211, and theta was 133.9. All right, we've got one more example here, and this one's a bit more abstract. I'm going to section off the work, kind of snuck down into example 4. In example 4, let me start fresh here. In example 4, it says, find the resultant force on Q in terms of K, Q, and A. So, actually what this should say is find the resultant force on Q. The other Q's are the same amount, but a lowercase q, so I apologize. This is a typo. That should be a lowercase q. So what I'm going to do is I'm going to think about what forces are on this positive Q in the lower right-hand corner. And what I notice is that it's the only positive charge. It's attracted to the top charge. It's attracted to the charge in the corner, and it's attracted to the charge on the right. So I'm going to have to actually add those three vectors together. And to add them together is going to look something like this. Oops. And what I'm going to need is I'm going to need the components of this diagonal vector. So I can do that because what I have here is I have a square cut by a diagonal, and I know that the angles in this square, or the angle of this diagonal, is 45 degrees. I also remember some stuff about 45, 90 right triangles, so I'm going to review that right now. So if I have a triangle that's 45, 45, 90 with two sides, which I'll call x, then I know that the hypotenuse is x times the square root of 2. And that's because x squared plus x squared equals c squared, if I use the Pythagorean theorem. 2x squared equals c squared. So c is going to equal the square root of 2x if I take the square root of both sides. So I'm going to come back to this fact. It's going to come in really handy. Okay, before I do that though, I need to figure out how big are these forces. I'm going to start with this up force. And I'm going to plug into Coulomb's law. So I have that force is kq squared over a. Then I'm going to do the sideways force. It's the same amount. F equals kq squared over a squared. For the diagonal force, I've got kq squared on the top. This distance here is the square root of 2 times a. So that's what goes in the denominator. And when I simplify that, I get kq squared over 2a squared. And it's at 45 degrees. Now, to find the components of that, to find the horizontal and vertical components, I could go to decimals and use sine and cosine. I'm going to use this special right triangle knowledge instead. I'm going to take this hypotenuse and divide by the square root of 2 to get this horizontal and vertical components. Okay, then finally, to find the answer, to find the sum of these three vectors, what I have to do is take the horizontal component and add it to the vertical component. So I've drawn that here. The horizontal component, if I go back, I'm going to switch colors. If I go back and look at the horizontal that I have and this horizontal that I have, I can add those together. Kq squared over a squared plus kq squared over 2 times the square root of 2a squared. And then in the vertical direction, it's the same thing. And then what I did next was I factored. I made this into a proper or a more, no, I made this into something with the same denominator. So when I factored out kq squared over a squared, instead of calling this 1, I'm going to call it this 2 times the square root of 2 over 2 times the square root of 2, because that allows me to simplify or combine. And now I know that if I know how long one of these sides is, to get the hypotenuse, because I'm still working with a 45, 45, 90 right triangle, I know that all I have to do is multiply the side, either one of these sides, times the square root of 2 to get my result. And when I do that, the square root of 2 actually drops out, and I end up with 2 times the square root of 2 plus 1 over 2 times kq squared over a squared. Oof, that was quite a lot of algebra and quite a lot of special right triangles. So let me know if you have any questions, and I'll see you in class.